As you see, I'm calling this exponents and radicals. Of course, radicals means things like square roots, cube roots, fourth roots. And from previous courses, of course, you remember there's a relationship between exponents and radicals, and certain kinds of exponents mean that we have a square root or a cube root involved. But I first want to remind you, and of course it's more how we deal with these exponents and these radicals in a course of this type. And what I want to remind you first about is exponents that are negative. And so let's first think of that situation. And you recall, that's the big deal here. Negative exponents, if we have something that looks, well, the rule states this: a to the power negative n is 1 over a to the power positive n. And this is kind of assuming that n is a positive number. So, of course, examples of what that would mean is if we had 3 to the power negative 2, that's the same as 1 over 3 to the power positive 2, and of course that's 1/9. And so negative exponents don't mean we have a negative answer. It means that our answer probably involves a fraction. And of course, that would apply to things that if we saw x to the power negative 1, then we recognize, of course, that just means 1 over x. Now, the issue that I want to involve you with here is that we're used to looking at numbers to negative powers or just to powers and variables themselves, that is, just letters to powers. But rules of exponents also apply to expressions. In other words, we might have something that looks like x squared plus 1, and we might have a power of negative 3 on that. Well, we like to write without negative exponents normally. And so that power of negative 3 applies to the whole expression x squared plus 1. And so the way we would write that without a negative exponent, of course, is 1 over x squared plus 1 to the positive 3 power. So we need to get used to that idea. Now, also, it's not uncommon that we want to work backwards. Sometimes we don't like things in a fractional form. And so we might be faced with something that looks like 1 over 2x plus 3 to a power of 5. See, it might look like that. And we may be asked to write that so that we do not have a fraction. And the way we could do that is just more or less think backwards. How do we get a 5 exponent on bottom? Well, that's if we had a negative 5 exponent on top, wouldn't we? So we can kind of take the backwards path here. And we'll find out later in the course that the second form is more useful to us than the first form. But when we leave a final answer, we like to write it without negative exponents. So we need to be able to go back and forth as I'm showing here. Now we also need to remember that if we see something that looks like 3 times x to the negative 4, we have to be careful. If we want to write that without negative exponents, we have to understand what that negative 4 exponent applies to. And a common mistake, a common mistake is to say, oh, 3x to the negative 4 is 1 over 3x to the 4th. But that's a mistake, because the issue is that negative 4 exponent doesn't have anything to do with the 3. And so that negative 4 exponent doesn't affect the position of the 3. And I know you remember this, but I'll emphasize this by saying, oh, this is really 3 times x to the negative 4 power. And it's only that x to the negative 4 power that is rewritten as 1 over x to the 4th. And so this is really just 3 over x to the 4th power. So it's only the x that got moved. Okay, so be careful. That is not true what we wrote over here. You can't do that. Let's see, what else do I want you to know of? Oh, well, we're used to this. we're used to this idea. And let me show you why this works, because we have to be careful at times with applying rules that we think are true but aren't really true. But let's take this example, and what I want to do is write it without negative exponents. So write without negative exponents. Okay, let's see. Let's see the expression as a fraction, and maybe the numerator is 3x to the negative 1 times y to the second over 5, let's say w to the third power times z to the negative fourth power. Okay, I know that's awful messy looking, but I'm wanting to illustrate what happens. And I think that what you recognize is that we're going to move the x factor down and the z factor up. And I think probably you've been taught that in the past. So what I'm thinking that you recognize is that to change that negative 1 exponent on the x to a positive, we move it below. And so below it becomes x to the first. Now, we have a y squared on top, and we don't need to change that exponent, so it stays on top. And we have a w cubed on bottom, and it's a positive exponent, so it doesn't change. But that z to the negative fourth is a negative exponent, and we need to affect a change in it, and so we move it up to the top, and when we do, it becomes z to the fourth. And that is, in fact, true. But let me show you why it's true so that we'll understand in another type of problem that we have to be careful. So by actual definition of what these exponents mean, this becomes 3 times 1 over x, that's x to the negative 1, times y squared. And on the bottom, we have a 5 times a w cubed times 1 over z to the positive 4. Now, when we look at that, on the top, we really have a fraction that is 3y squared divided by x. And on bottom, we really have a fraction, which is 5w cubed divided by z to the fourth. Now, when we have a fraction divided by a fraction, which we're showing here, then that's nothing more than what we're dividing into times the reciprocal of our divisor. So instead of saying divide by that fraction, we say multiply with its reciprocal. And then as we do that multiplication, you see that it ends up on top just as a 3y squared z to the fourth, and on bottom, of course, a 5 times an x times a w cubed. And we, with all that work, we got the result that we had decided over here by just moving across the division bar. Now, this works only, see, this idea of moving across the division bar causes a change in the sign of the exponent, works only if the operations are multiplication and, of course, the division that we see already. Okay. It doesn't work if we have additions or subtractions involved. And so I want to go to the next page and give you a kind of a little idea there. You will have some homework problems in which you'll practice this. Okay, here is the example. We're asked to simplify x to the negative 1 plus y to the negative 1. And in this case, what we mean is write it without negative exponents. And, you know, the idea that we create fractions with these exponents that are negative is at play here. But this is not 1 over x plus y. See, we might be tempted to say we're tempted to say, oh, well, these negative exponents. So we just simplify this as 1 over x plus y. But that's not correct. And it's because we have an addition involved, we can't start moving across an imaginary division line here. So we have to have another approach. And our approach is we go back to what in the world do these negative exponents mean? And so in this case, x to the negative 1 by itself is 1 over x. And y to the negative 1 by itself is 1 over y. And of course, we don't add together fractions by adding their denominators. This isn't 1 plus 1 over x plus y. If we were to add these, we'd have to get a common denominator. And that common denominator, that lowest common denominator in this case, would be x times y. So if we were actually going to add these together, we would take this first fraction and would multiply on top by y and on bottom by y. And we'd have to take this second fraction and multiply on top by x and bottom by x so that we have an xy denominator. So our first fraction would be 1 times y on top and x times y on bottom. Okay, or yx, I guess we could write. And in the second fraction, we'd have x times 1 on top, that's x, and x times y on bottom. And so when we actually add these together, we get y plus x over xy. So you notice here, of course, it wasn't quite so simple, and it's because of the addition along with negative exponents. That requires that we be more careful and we approach these problems differently. Now, I want to go back to dealing with exponents. Okay, dealing with exponents. When we have expressions involved rather than just letters. But let me remind you for each of these that if we looked at an example and we said, let's multiply x to the 5th times x, we recognize that's x to the power of 5 plus 1. And it's because we have x's times x's, and of course that's x to the 6th. What I'm wanting you to correspond that with, and notice that it really doesn't matter what the powers are on as long as it's the same base. That is, the powers are on the same type of thing. So we might have x squared plus 1 with a power of 5 on it times just an x squared plus 1. And we understand that x squared plus 1 is involved in both of these. One time we have an exponent of 5, and the other time we have an exponent of 1. So this is really x squared plus 1 to the power of 5 plus 1. Of course, we would do that in our head, and would say that's x squared plus 1 to the power 6. Now, we also know how to deal with things that look like x to the 5th power over x to the 2nd power. In that scenario, we take x and create a new power on it that's the top power, minus the bottom power. In this case, that's x cubed. And we can do that same thing if we even have expressions. So we might have something like 2x plus 4 to the power of 5 on top, divided by 2x plus 4 to the power of 2 on bottom. And since the bases are the same, their bases in both cases are 2x plus 4, and the base is what the power is applying to, then we know that that really is just going to be calculated as a new power on 2x plus 4. We're going to take the exponent 5, subtract the exponent 2, and so that simplifies to 2x plus 4 to the 3rd power. Now, going back to the kind of problem that we said that we can move things across the division bar, we might be dealt something like this. Simplify, and we might have, let's say, x squared times x squared plus 3 to the power negative 4 times, let's just say 2x minus 1. And that's divided by, let's see, in this case, maybe we have 3x plus 5 to the power negative 2. Now, in this case, simplify means deal with those negative exponents. Now, here we see additions and subtractions, but the exponents apply to things that are in parentheses, don't they? And the only additions and subtractions are in parentheses, and we think of parentheses as units themselves. So we have no operations except inside parentheses that are addition and subtraction. So we can deal with this just like multiplications. That is, the x squared that we have over here has a positive 2 exponent on it, and so that doesn't go anywhere. If we try to move it, we change the exponent to negative. And the 2x minus 1 has an understood exponent of 1 on it, and we don't want to move that anywhere, otherwise we would end up with a negative 1 exponent. It's that negative 4 exponent on top, and we can effect a change there by moving it across the division bar. So when we move that factor across the division bar, the exponent becomes positive 4. Now on the other hand, we have what's on the bottom, and we need to change that exponent from a negative 2 to a positive 2, so we have to move it up above the division bar, and so on top it becomes 3x plus 5 to the positive 2 power. And now we've written the expression with no negative exponents. So that idea works even when we have expressions with exponents on them rather than just letters with exponents. Okay, on the next page, I think what I would like to do is now remind you about another kind of exponent, and that is one that we call a rational exponent, and what its relationship to radicals are. So let's pause as I set up the next page. So rational exponents mean exponents that are fractions. Fractional exponents. I'm not sure again that you remember this. So we might be faced with something that looks like 16 to the power 1/2. And if you recall, that means the square root of 16, doesn't it? So in this case, we actually have a 4. Or we might be faced with something like 8 to the power 1/3. And if you recall, that means the cube root of 8. And of course, the cube root of 8 is 2. And so as a reminder, what the rule really says is if we have a to a power that is 1 over n, that means that's the same thing as the nth root of a. That's really what I've applied over here. Now, that's just special kinds of fractions. That's 1 over 2, 1 over 3, 1 over 5. Oh, and by the way, while we're here, suppose we had, let's say, 16 to the power negative 1/4. Well, before we can apply any kind of radical or any special meaning of this power 1/4, we first have to deal with the negative exponent. And so before we could go further, we'd have to say, well, that's 1 over 16 to the positive 1/4 power. Now we can deal with the fact that we have a positive 1/4 power. That means the 4th root of 16. So we have 1 over the 4th root of 16, and we happen to know that the 4th root of 16 is 2, so this is really a 1/2. Now, as I was mentioning, these are exponents that are just 1 over, 1 over, 1 over. And of course, we might have exponents that are, it looks something like, we'll say 16 to the power 3/4 as an example. It's not always our exponent is 1 over. And the idea behind this is, and we'll come back and we'll figure out what that is in just a moment. Or maybe we have 8 to the power, I don't know, how about 5/3? See, something that looks like that. What would that be equal to? Well, it's a play on information we already know. And so we'll talk specifically, or, what happens if we have an exponent that is some number other than 1 divided by some other number. And the way we deal with this is we think in there's 2 ways to think about it. Whoops, that's an ugly brace. Sorry about that. There's 2 ways for us to think about this. We can think of this as a to the power 1 over n, and that raised to the power m, because 1 over n times m, of course, is the fraction m over n. And what we have on the inside, that 1 over n power says we have the nth root of a, and what we have on the outside is the power m. So we can think of that rational exponent saying we need to take an nth root, and after we take the nth root, we'll raise it to the mth power. Now, on the other hand, we could have said that that's a to the m power, and that raised to the power of 1 over n, because after all, we'd multiply those exponents together, and we'd still have m over n. And so this says we're having the nth root of a to the m. See, that exponent is on the a, so it would be the nth root of a to the n. Now, the issue is that these are identical. Those are the same thing. It's just 2 different ways for us to interpret. And sometimes one interpretation is better than the other, or vice versa. So if we go back to the 2 examples we saw, see, we could write this 16 to the 3/4. We could say that that's the 4th root of 16 with the exponent of 3 on that. Pardon me. Or we could say that it's the 4th root of 16 to the 3rd. Now, the second option there is equivalent to the top option. Okay, the bottom is equivalent to the top. But the top option is easy for us to deal with, because the 4th root of 16 is 2, and so we're cubing a 2, which is nothing more than 8. On the bottom, we'd have to figure out what 16 cubed is before we could deal with the 4th root. So we prefer, in this case, the top interpretation. And also in this second situation, 8 to the 5/3 power, we would probably prefer as well that we think in those ways, that we'll have a cube root of 8, and that cube root is raised to the 5th power. Well, the cube root of 8 is 2, so we have 2 to the 5th power, and 2 to the 5th power happens to be 32. Now, one thing I guess I need to mention before we go is that I don't want you to get mixed up with rules of exponents, and here's what I mean by that. We've learned in the past that if we have, say, as an example, the square root of 4x to the 3rd power, that rules of exponents allow us to think of that as the square root of 4 times the square root of x cubed. Okay, we're allowed to think of it that way. And the reason we want to think of it that way is the square root of 4 we know is 2. So this becomes 2 times the square root of x cubed. And then we have the issue that we can think of the square root of x cubed. We can think of that x cubed as x squared times x. And so that allows us to think 2 times square root of x squared times square root of x. And then, of course, we know square root of x squared, if x is positive, is just x. And so it simplifies to 2x times square root of x. But the main issue is this first step. When we have multiplication here, we can break it into multiplication of 2 radicals. But that's different than if we have something like the square root of x squared plus 4. That's not equal to the square root of x squared plus the square root of 4. we can't break things apart with addition or subtraction. And an easy example of that is you happen to know, let's see, if we had the square root of, say, 16 plus 9, well, of course, the square root of 16, the 16 plus 9 is actually 25, and so we know this result is 5. But if you tried to break this apart and say that's the square root of 16 plus the square root of 9, well, the square root of 16 is 4, the square root of 9 is 3, and that would be 7. And so something's awry, and what's awry is that first step. We can't break square roots apart by additions or subtractions. So what we've looked up here is we can only deal with that when we're talking about multiplications. Now, I guess the last thing I want you to be aware of, and the kind of practice that I want you to be able to do, is changing radical expressions into rational exponent expressions. So let me set things up on the next page. I had a little change of heart here, and you see that I'm saying change each expression to radical form. And so we might see something that looks like 6x to the power 3/5. Now, we're going to change that to radical form so we don't have any exponents of fractional type. And when we do that, we normally are thinking in these terms, that a to the power m over n will normally, we don't have to write it this way, but we'll think of that as terms of the nth power of a to the m. So we'll keep all of our exponents around the radical instead of outside that radical. So a common mistake here is to put the 6x underneath the radical, but I'm going to overemphasize what this means, and it's kind of like we dealt with negative exponents a while ago. That exponent 3/5 has nothing to do with the 6. So that 6 is kind of a separate issue here, isn't it? Now, the x to the 3/5, if we write that in radical form, it's the 5 that is the denominator, tells us the index of the radical. So it's a 5th root. And the 3 in the numerator of the exponent ends up being a regular exponent on the radicand. So this is really 6 times the 5th root of x cubed. Now, we might have something similar to that we might have a situation where it looks like x squared times 3x minus 1 to a power of 1/2. See, we might have something that looks that way. And if we're going, the only thing that's going to invoke the idea of a radical form is that exponent of 1/2. And so we need to recognize that 1/2 exponent applies to the 3x minus 1. It has nothing to do with the x squared. So the x squared is a separate issue from the radical. Now, the 1/2 power means we have a square root, and it's the square root of what the power is on. And in this case, that power is 3x minus 1. So we would write our radical form as x squared times the square root. If we happen to have something that looked like, I don't know, x to the 1/2 power plus y to the 1/2 power. Well, but one 1/2 power applies to x and the other to y. The first is the square root of x, and the second is the square root of y. And we can't bring square roots together that are being added by adding underneath. And so that's the final way we would have to leave that answer. So just make sure that we don't make silly mistakes. Now, what I do want to do next is what we'll be faced with probably more frequently in this class. And that's to change each expression to rational exponent form. So we're going to change to, I'm just going to say exponent form. And we'll probably do this quite a bit, actually. And so if we saw 6 6 times the square root of x, we know to change that to exponent form, that square root would be written as a power of 1/2, and it's on the x. Now, that's a little different than the square root of 6x. In that case, the square root, we're changing to exponent form. Since the square root of 6x, the exponent is going to have to be on 6x. So a little different look between those two scenarios. Now, again, I'm very much interested in us dealing with things that look like the square roots of more complicated expressions. So if we had the square root of x cubed plus 3x plus 2, then to change that to exponent form, what's under the radical is what's going to have the exponent on it. So x squared plus 3x plus 2 will have an exponent of 1/2 on it. Now, of course, it can get more complicated. We might have the cube root of x to the second power. Okay, well, if we're going to change that to exponent form, we've got to recognize that, of course, somehow or another, one thing we could do is we could say, well, that cube root means we have a power of 1/3. And that power of 1/3 goes on what's underneath the radical. And then we have that expression where we can multiply the two exponents, and we can see that the exponent that we would have would be 2/3, and that's the way we would write it. And now when we see that, we can imagine it going there directly because we understand what a 2/3 exponent means. And we might have skipped that step once we recognize the situation. Let's do one more here. We want to write, let's say the square root of x squared plus 1 to the power 3, something that looks that way. Now, we can kind of do what we did on the previous step. That is, we can apply the square root, we can change the square root into an exponent. And so what we're going to have, let's imagine this, we're going to have an exponent of 1/2, and that's because of the square root. And what that square root is of is something that's kind of complicated. It looks like that, doesn't it? So that 1/2 means we have the square root of what's inside. And now these exponents 3 right here and 1/2 right there are going to be multiplied together. And so that will create an exponent. 3 times 1/2 is 3/2. Now, an exponent, never can we distribute an exponent, if you will. That plus inside the parentheses says, no, we can't make that exponent 3/2 go to the x squared and also go to the 1. It goes to the whole thing, x squared plus 1. And so this is the way we would end up leaving our answer. It would have to be pretty familiar or pretty confident in that. Let's see, I think for now that's good enough. We've done a lot of review in this section and in others. I think there's, well, let's stop this for now. We'll get plenty of practice when we start actually doing the calculus portion.